Hello everyone. So today we'll be doing the audiobook of Class 12 CBSE Chapter 2 Electrostatic Potential and Capacitance. So please give this a thumbs up and please do subscribe our channel for more contents. So I would highly suggest you to keep your NCERT books in front of you while I read. Chapter 2 Electrostatic Potential and Capacitance. 2.1 Introduction. In chapters 6 and 8, class 11, the notion of potential energy was introduced. When an external force does work in taking a body from a point to another against a force like spring force or gravitational force, that work gets stored as potential energy of the body. When the external force is removed, the body moves, gaining kinetic energy and losing an equal amount of potential energy. The sum of kinetic and potential energies is thus conserved. Forces of this kind are called conservative forces. Spring force and gravitational force are examples of conservative forces. Coulomb's force between two stationary charges is also a conservative force. It is not surprising since both have inverse square dependence on distance and differ mainly in the proportionality constants. The masses in the gravitational law are replaced by charges in Coulomb's law. Thus, the potential energy of a mass in a gravitational field, we can define electrostatic potential energy of a charge in an electrostatic field. Consider an electrostatic field vector E due to some charge configuration. First, for simplicity, consider the field E due to a charge capital Q placed at origin. Now imagine that we bring a test charge small q from a point R to a point P against the repulsive force of it on it due to the charge capital Q. With reference to figure 2.1, this will happen if capital Q and small q are both positive or both negative. For definiteness, let us take capital Q, small q greater than 0. Two remarks may be made here. First, we assume that the test charge small q is so small that it does not disturb the original configuration, namely the charge capital Q at the origin, or else we keep capital Q fixed at the origin by some unspecified force. Second, in bringing the charge small q from R to P, we apply an external force F external just enough to counter the repulsive electric force Fe. That is, F external is equal to minus Fe. This means that there is no net force on or acceleration of the charge small q when it is brought from R to P. It is brought with infinitesimally slow constant speed. In this situation, work done by external force is a negative of the work done by electric force and gets fully stored in the form of potential energy of the charge q. If the external force is removed on reaching P, the electric force will take the charge away from capital Q. The stored energy, that is potential energy at P, is used to provide kinetic energy to charge small q in such a way that sum of the kinetic and potential energies is conserved. Thus, work done by external forces in moving a charge small q from R to P is WRP is equal to integral R to P F external into delta R is equal to minus integral R to P F E into dr. This work done is against electrostatic repulsive force and gets stored as a potential energy. At every point in electric field, a particle with charge small q possesses a certain electrostatic potential energy. This work done increases its potential energy by an amount of equal to potential energy difference between 2 points R and P. Thus, potential energy difference delta U is equal to UP minus UR is equal to WRP. Note here that this displacement is an opposite sense to the electric force, and hence work done by electric field is negative, that is minus WRP. Therefore, we can define electric potential energy difference between the 2 points as work required to be done by an external force in moving, that is without acceleration, a charge q from one point to another for electric field of an arbitrary charge configuration. Two important comments may be made at this stage. 1. The right side of equation 2.2, that is delta Q is equal to Qp minus Qr is equal to WRP, depends only on the initial and the final positions of the charge. It means that the work done by an electrostatic field in moving a charge from one point to another depends only on the initial and the final points, and it is independent of the path taken to go from one point to another. This is the fundamental characteristic of a conservative force. The concept of potential energy would not be meaningful if the work depended on the path. The path independence of work done by an electrostatic field can be proved using Coulomb's law. We omit this proof here. 2. Equation 2.2, that is delta U is equal to UP minus UR is equal to WRP, defines potential energy difference in terms of physically meaningful quantity work. Clearly, potential energy so defined is undetermined to within an additive constant. What this means is that actual value of potential energy is not physically significant. It is only the difference of potential energy that is significant. We can always add an arbitrary constant alpha to potential energy at every point, since this will not change the potential energy difference. That is, UP plus alpha whole bracket minus UR plus alpha whole bracket is equal to UP minus UR. Put it differently, there is a freedom in choosing the point where potential energy is 0. A convenient choice to have electrostatic potential energy 0 at infinity. With this choice, we take the point R at infinity. We get from equation 2.2 W infinity P is equal to UP minus U infinity is equal to UP only. Since the point P is arbitrary, equation 2.3 provides us with a definition of potential energy of a charge small q at any point. Potential energy of charge q at a point in the presence of field due to any charge configuration is a work done by external force that is equal and opposite to the electric force in bringing the charge from small q from infinity to that point. 2.2 Electrostatic potential. Consider any general static charge configuration. We define potential charge of a test charge small q in terms of work done on the charge q. This work is obviously proportional to q, since the force at any point is QE, where E is the electric field at that point due to the given charge configuration. It is therefore convenient to divide the work by the amount of charge small q, so that the resulting quantity is independent of q. In other words, work done per unit test charge is characteristic of electric field associated with a charge configuration. This leads to the idea of electrostatic potential V due to a given charge configuration. From equation 2.1 we get work done by an external force in bringing a unit positive charge from point R to P is equal to Vp minus Vr is equal to Up minus Ur whole divided by Q, where Vp and Vr are the electrostatic potentials at P and R respectively. Note as before that it is not the actual value of potential but the potential difference that is physically significant. If as before we choose the potential to be 0 at infinity, equation 2.4 implies work done by an external force in bringing a unit positive charge from infinity to that point is equal to electrostatic potential V at that point. In other words, electrostatic potential V at any point in a region with electrostatic field is the work done in bringing a unit positive charge without acceleration from infinity to that point. The qualifying remarks made earlier regarding potential energy also apply to the definition of potential. To obtain the work done per unit test charge, we should take an infinitesimal test charge delta Q, obtain the work done delta W in bringing it from infinity to the point, and determine the ratio delta W by delta Q. Also, the external force at every point of the path is to be equal and opposite to the electrostatic force on the test charge at that point. 2.3 Potential due to a point charge. Consider a point charge capital Q at the origin. Figure 2.3. For definiteness, take capital Q to be positive. We wish to determine the potential at any point P with position vector r from the origin. For that, we must calculate the work done in bringing a unit positive test charge from infinity to point P. For capital Q greater than 0, the work done against the repulsive force on the test charge is positive. Since work done is independent of the path, we choose a convenient path along the radial direction from infinity to the point P. At some intermediate point P dash on the path, the electrostatic force on a unit positive charge is capital Q into 1 divided by 4 pi epsilon 0 r dash square into r dash cap, where r dash cap is the unit vector along OP dash. Work done against this force from r dash to r dash plus delta r dash is delta W is equal to 1 by 4 pi epsilon 0 minus Q by r dash square into delta r dash. The negative sign appears because for delta r dash less than 0, delta W is positive. Total work done W by external forces obtained by integrating equation 2.6, that is delta W is equal to minus Q by 4 pi epsilon 0 r dash square into delta r dash from r dash is equal to infinity to r dash is equal to r. W is equal to minus integral of infinity to r 1 by 4 pi epsilon 0 Q by r dash square into dr dash is equal to Q by 4 pi epsilon 0 r dash limits infinity to r is equal to Q by 4 pi epsilon 0 r. By definition is the potential at P due to the charge capital Q. V of r is equal to 1 by 4 pi epsilon 0 Q by r. Equation 2.8, the previous equation, is true for any sign of the charge Q, though we considered capital Q greater than 0 on its derivation. For capital Q less than 0, V less than 0, that is work done by external force per unit positive test charge in bringing it from infinity to point is negative. This is equivalent to saying that work done by electrostatic force in bringing the unit positive charge from infinity to the point P is positive. This is as it should be, since for capital Q less than 0, the force on a unit positive test charge is attractive, so that the electrostatic force and the displacement from infinity to P are in the same direction. Finally, we note that equation 2.8 is consistent with the choice that potential at infinity be 0. Figure 2.4 shows how the electrostatic potential, which is inversely proportional to R, and the electrostatic field, which is inversely proportional to r square, varies with the r. Refer figure 2.4. 2.4 Potential due to an electric dipole. As we learnt in last chapter, an electric dipole consists of two charges q and minus q separated by a small distance 2a. Its total charge is 0. It is characterized by a dipole moment vector p, whose magnitude is q into 2a and which points in the direction from minus q to q. We also saw that the electric field of a dipole at a point with the position vector r depends not only just on the magnitude of r but also on the angle between r and p. Further, the field falls off at a large distance, not as 1 by r square, typical field due to a single charge, but as 1 by r cube. We now determine the electric potential due to a dipole and contrast it with the potential due to single charge. As before, we take the origin at the center of the dipole. Now we know that the electric field obeys the superposition principle. Since potential is related to the work done by the field, electrostatic potential is also follows the superposition principle. Thus, the potential due to the dipole is the sum of potentials due to charge q and minus q. V is equal to 1 by 4 pi epsilon 0 q by r1 minus q by r2, where r1 and r2 are the distances of the point P from q and minus q respectively. Now by geometry, r1 square is equal to r square plus a square minus 2ar cos theta. r2 square plus r square is equal to a square plus 2ar cos theta. We take r much greater than a, that is r very much greater than a, and retain terms only up to the first order in a by r. So r1 square is equal to r square into 1 minus 2a cos theta divided by r plus a square divided by r square, approximately equal to r square into 1 minus 2a cos theta divided by r. Similarly, r2 square approximately equal to r square into 1 plus 2a cos theta divided by r. Using the binomial theorem and retaining terms up to the first order a by r, we obtain that 1 by r1 approximately equal to 1 by r into 1 minus 2a cos theta divided by r raised to 1 minus 1 by 2 is approximately equal to 1 by r into 1 plus a by r cos theta. 1 by r2 is approximately equal to 1 by r into 1 plus 2a cos theta by r raised to minus 1 by 2, which is equal to 1 by r into 1 minus a by r cos theta. Using equations 2.9 and 2.13 and p is equal to 2qa, we get that v is equal to q divided by 4 pi epsilon 0 2a cos theta divided by r square is equal to p cos theta divided by 4 pi epsilon 0 r square. Now p cos theta is equal to vector p into r cap, where r is the unit vector along position vector OP. The electric potential of a dipole is then given by V is equal to 1 by 4 pi epsilon 0 P divided by r square into r cap, where r is very much greater than a. Equation 2.5 is as indicated approximately true only for distances large compared to the size of the dipole, so that the higher order terms in a by r are negligible. For a point dipole P at the origin, equation 2.15 is however exact. From equation 2.15, potential on the dipole axis when theta is equal to 0 pi is given by V is equal to 1 by 4 pi epsilon 0, which is plus or minus P divided by r square. Positive sign for theta is equal to 0, negative sign for theta is equal to pi. The potential in the equatorial plane, theta is equal to pi by 2, is 0. The important contrasting features of an electric potential of a dipole from that due to a single charge are clear from equations 2.8 and 2.15. 1. The potential due to a dipole depends not just on r but also on the angle between the position vector r and the dipole moment vector p. It is, however, axially symmetric about p. That is, if you rotate the position vector r about p, keeping theta fixed, the points corresponding to p on the cone so generated will have the same potential as p. 2. The electric dipole potential falls off at large distance, that is 1 by r square, not as 1 by r, characteristic of the potential due to single charge. You can refer to figure 2.5 for graph of 1 by r square versus 1 by versus r and 1 by r versus r drawn there in another context. Potential due to a system of charges 2.5. Consider a system of charges q1, q2, etc. qn with the position vectors r1, r2, etc. rn related to some origin as mentioned in figure 2.6. The potential v1 at p due to the charge q1 is v1 is equal to 1 by 4 pi epsilon 0 q1 divided by r1p, where r1p is the distance between q1 and p. Similarly, potential v2 at p due to q2 and v3 due to q3 are given by v2 is equal to 1 by 4 pi epsilon 0 q2 divided by r2p, v3 is equal to 1 by 4 pi epsilon 0 q3 divided by r3p, where r2p and r3p are the distances of p from charges q2 and q3 respectively, and so on for the potential due to other charges. By superposition principle, potential V at P due to the total charge configuration is the algebraic sum of potentials due to individual charges. That is, V is equal to V1 plus V2 plus etc. plus Vn plus 1 by 4 Q1 by R1P is equal to Q2 by R2P is plus etc. Qn by Rnp. If we have a continuous charge distribution characterized by a charge density rho of R, we divide it as before into small volume elements each of size delta R, delta V, and carry a charge rho into delta V. We then determine the potential due to each volume element and sum, strictly speaking integrate over all such contributions and thus determine the potential due to entire distribution. We have seen in chapter 1 that for a uniformly charged spherical shell, the electric field outside the shell is as if the entire charge is concentrated at the center. Thus potential outside the shell is given by V is equal to 1 by 4 pi epsilon 0 Q by R, where small r is greater than or equal to capital R, where small q is the total charge on the shell and r is its radius. The electric field inside the shell is 0. This implies that potential is constant inside the shell as no work is done on moving charge inside the shell. Therefore, equals its value at the surface, which is 1 by 4 pi epsilon 0 q by capital R. 2.6 Equipotential surface. An equipotential surface is a surface with a constant value of potential at all points on the surface. For a single charge small q, the potential is given by equation 2.8. That is, V is equal to 1 by 4 pi epsilon 0 q by R. This shows that V is a constant if R is a constant. Thus, equipotential surface of a single point charge are concentric spherical surfaces centered at the charge. Now, electric field lines for a single charge q are radial lines starting from one end at the charge depending on whether small q is positive or negative. Clearly, the electric field at every point is normal to the equipotential surface passing through that point. This is true in general. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. The proof of this statement is very simple. If the field were not normal to the equipotential surface, it would have non-zero component along the surface. To move a unit charge against the direction of the component of the field, work have to be done. But this is in contradiction to the definition of an equipotential surface. There is no potential difference between any two points on the surface, and no work is required to move a test charge on the surface. Electric field must therefore be normal to the equipotential surface at every point. Equipotential surfaces offer an alternative visual picture in addition to the picture of electric field lines around the charge configuration. For a uniform electric field E, say along the x-axis, the equipotential surfaces are planes normal to x-axis, that is planes parallel to YZ plane. Equipotential surface for A dipole, and B, two identical positive charges, are shown in figure 2.11. Relation between field and potential. Consider two closely spaced equipotential surfaces A and B with potential values V and V plus delta V, where delta V is the change in V in the direction of the electric field E. Let P be the point on the surface B. Delta L is the perpendicular distance of surface A from P. Imagine that a unit positive charge is moved along its perpendicular from the surface B to surface A against electric field. The work done in this process is magnitude of E into delta L. This work equals the potential difference VA minus VB. Thus, magnitude of E into delta L is equal to V minus whole bracket V plus delta V is equal to minus delta V. E is equal to delta V, that is minus delta V divided by delta L. Since delta V is negative, delta V is equal to minus of modulus delta V. We can rewrite this as modulus E is equal to minus delta V by delta L is equal to plus modulus delta V by delta L. We thus arrive at two important conclusions concerning the relation between electric field and potential. Electric field is in the direction in which the potential decreases steepest. Its magnitude is given by the change in the magnitude of potential per unit displacement normal to the equipotential surface at point. 2.7 Potential energy of a system of charges. Consider first a simple case of two charges q1 and q2 with position vector r1 and r2 relative to some origin. Let us calculate the work done externally in building up this configuration. This means that we consider the charges q1 and q2 initially at infinity and determine the work done by the external agency to bring the charges to the given locations. Suppose first the charge q1 is brought from infinity to point r1. There is no external field against which work needs to be done. So work done in bringing q1 from infinity to r1 is 0. This charge produces a potential in space given by V1 is equal to 1 by 4 pi epsilon 0 q1 divided by r1p, where r1p is the distance of a point P in space from location of q1. From the definition of potential, work done in bringing charge q2 from infinity to point r2 is q2 times the potential at r2 due to q1. That is, work done on q2 is equal to 1 by 4 pi epsilon 0 q for q1 q2 divided by r12, where r12 is the distance between points 1 and 2. Since electrostatic force is conservative, this work gets stored in the form of potential energy of the system. Thus, the potential energy of system of two charges q1 and q2 is capital U is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r12. Obviously, if q2 was brought first to its present location and q1 brought later, potential energy V would be the same. More generally, the potential energy expression equation 2.22 is unaltered whatever way the charges are brought to the specified locations because of path independence of work for electrostatic force. Equation 2.2 is true for any sign of q1 and q2. If q1 q2 greater than 0, potential energy is positive. This is as expected since for like charges, that is q1 q2 greater than 0, electrostatic force is repulsive and a positive amount of work is needed to be done against the force to bring the charges from infinity to a finite distance apart. For unlike charges q1 q2 less than 0, electrostatic force is attractive. In that case, positive amount of work is needed against this force to take the charges from the given location to infinity. In other words, a negative amount of work is needed for the reverse path from infinity to the present location so that the potential energy is a negative. Equations 2.22 is easily generalized for a system of any number of point charges. Let us calculate potential energy of a system of 3 charges q1, q2 and q3 located at r1, r2 and r3 respectively. To bring q1 first from infinity to r1, no work is required. Next we bring q2 from infinity to r2. As before, work done in this step is q2 v1 with respect to r2 is equal to 1 by 4 pi epsilon 0 q1 q2 divided by r12. Charges q1 and q2 produce a potential which at any point p is given by v12 is equal to 1 by 4 pi epsilon 0 q1 by r1p plus q2 by r2p. Work done next in bringing q3 from infinity to point r3 is q3 times v12 at r3. q3 into v12 with respect to r3 is equal to 1 by 4 pi epsilon 0 bracket q1 q3 by r13 plus q2 q3 by r23. The total work done in assembling the charges at given locations is obtained by adding the work done in different steps. U is equal to 1 by 4 pi epsilon 0 bracket q1 q2 divided by r12 plus q1 q3 divided by r13 plus q2 q3 by r23. Again, because of the conservative nature of electrostatic force or equivalently the path independence of work done, the final expression for U is independent of the manner in which the configuration is assembled. Potential energy is characteristic of the present state of configuration and not the way the state is achieved. 2.8 Potential energy in an electric field. 2.8.1 Potential energy of a single charge. In section 2.7, the source of the electric field was specified. The charge and their locations and the potential energy of the system of those charges was determined. In this section, we ask a related but a distinct question. What is the potential energy of a charge small q in a given field? This question was in fact the starting point that led us to the notion of the electrostatic potential. But here we address this question again to clarify in what way it is different from the discussion in section 2.7. The main difference is that we are now concerned with the potential energy of a charge or charges in an external field. The external field E is not produced by the given charge or charges whose potential energy we wish to calculate. Electric field is produced by sources external to given charge or charges. The external sources may be known, but often they are unknown or unspecified. What is specified is the electric field E or the electrostatic potential V due to the external sources. We assume that the charge small q does not significantly affect the sources producing the external field. This is true if Q is very small or the external sources are held fixed by other unspecified forces. Even if Q is finite, its influence on the external sources may still be ignored in the situation when very strong sources far away at infinity produce a finite field E in the region of interest. Note that we are interested in determining the potential energy of a given charge Q and later a system of charges in the external field. We are not interested in the potential energy of the sources producing the external electric field. The external electric field E and the corresponding external potential V may vary from point to point. By definition, V at a point P is the work done in bringing a unit positive charge from infinity to point P. We continue to take potential at infinity to be 0. Thus, work done in bringing a charge Q from infinity to the point P in the external field is QV. This work is stored in the form of potential energy of small q. The point P has position vector r relative to some origin. We can write potential energy of q at r in an external field is equal to qv with respect to r, where Vr is the external potential at a point r. Thus, if an electron with a charge q is equal to E is equal to 1.6 into 10 raised to minus 19 coulomb is accelerated by a potential difference of delta V is equal to 1 volt, it would gain energy of q into delta V is equal to 1.6 into 10 raised to minus 19 joule. This unit of energy is defined as 1 electron volt or 1 eV. That is 1 eV is equal to 1.6 into 10 raised to minus 19 joule. The units based on eV are most commonly used in atomic, nuclear and particle physics. 1 kilo electron volt is equal to 10 raised to 3 electron volt is equal to 1.6 into 10 raised to minus 16 joule. 1 megavolt is equal to 10 raised to 6 electron volt is equal to 1.6 into 10 raised to minus 13 joule. 1 gigavolt is equal to giga electron volt is equal to 10 raised to 9 electron volt is equal to 1.6 into 10 raised to minus 10 joule, and 1 tera electron volt is equal to 10 raised to 12 electron volt is equal to 1.6 into 10 raised to minus 7 joule. This has already been defined on page 117 of class 11 physics part 1 table 6.1. 2.8.2 Potential energy of a system of two charges in an external field. Next, we ask, what is the potential energy of a system of two charges q1 and q2 located at r1 and r2 respectively in an external field? First, we calculate the work done in bringing the charge q1 from infinity to r1. Work done in this step is q1 v with respect to r1 using equation 2.27. Next, we consider the work done in bringing q2 to r2. In this step, work is done not only against the external electric field but also against the field due to q1. Therefore, work done on q2 against the external field is q2 into v with respect to r2. Work done on q2 against the electric field due to q1 is equal to q1 q2 divided by 4 pi epsilon 0 r12, where r12 is the distance between q1 and q2. We have made use of equations 2.27 and 2.22 by the superposition principle for fields. We add up the work done on q2 against the two fields E and that due to q1. Work done in bringing q2 to r2 is equal to q2v with respect to r2 plus q1 q2 divided by 4 pi epsilon 0 r12. Thus, potential energy of the system is equal to total work done in assembling the configuration is equal to q1 v of r1 plus q2 v of r2 plus q1 q2 divided by 4 pi epsilon 0 r12. 2.8.3 Potential energy of a dipole in an external field. Consider a dipole with the charges q1 is equal to plus q and q2 is equal to minus q placed in a uniform electric field E as shown in figure 2.1. 1.6. As seen in last chapter, in a uniform electric field, the dipole experiences no net force but experiences a torque tau given by tau is equal to P cross E, which will tend to rotate it unless P is parallel or anti-parallel to E. Suppose an external force tau external is applied in such a manner that it just neutralizes this torque and rotate it in the plane of paper from angle theta 0 to angle theta 1 at an infinitesimally angular speed and without angular acceleration. Amount of work done by external torque will be given by W is equal to integral theta 0 to theta 1 tau external of theta into d theta is equal to integral of theta 0 to theta 1 P E sin theta into d theta is equal to P E bracket cos theta 0 minus cos theta 1. This work is stored as a potential energy of the system. We can then associate potential energy U of theta with an inclination theta of the dipole. Similar to the other potential energies, there is a freedom in choosing the angle where the potential energy U is taken to be 0. A neutral choice is to take theta 0 is equal to pi by 2. An explanation for it is provided towards the end of discussion. We can then write U of theta is equal to Pe into cos pi by 2 minus cos theta is equal to Pe cos theta is equal to minus P dot E. This expression can alternately be understood also from equation 2.29. We apply equation 2.29 to the present system of two charges plus q and minus q. The potential energy expression then reads U dash of theta is equal to q into V r1 minus V into V of r2 whole bracket minus q square divided by 4 pi epsilon 0 into 2a. Here r1 and r2 denote the position vectors of plus q and minus q. Now the potential difference between the positions r1 and r2 equals the work done in bringing a unit positive charge against the field from r2 to r1. The displacement parallel to the force is 2a cos theta. Thus V of r1 minus V of r2 is equal to minus E cross 2a cos theta. Thus we obtain U dash of theta is equal to minus Pe cos theta minus q square divided by 4 pi epsilon 0 into 2a is equal to minus P dot E minus q square divided by 4 pi epsilon 0 into 2a. We note that U dash of theta differs from U of theta by a quantity which is just a constant for a given dipole. Since a constant is insignificant for potential energy, we can drop the second term in equation 2.34 and it then reduces to equation 2.32. We can now understand why we took theta 0 is equal to pi by 2. In this case, the work done against the external electric field in bringing plus q and minus q are equal and opposite and cancel out. That is, q of V of r1 minus V of r2 is equal to 0. 2.9 Electrostatics of conductors. Conductors and insulators were described briefly in chapter 1. Conductors contain mobile charge carriers. In metallic conductors, these charge carriers are electrons. In a metal, the outer or the valence electrons part away from their atoms and are free to move. These electrons are free within a metal but not free to leave the metal. The free electrons from a kind of gas, they collide with each other and with the ions and move randomly in different directions. In an external electric field, they drift against the direction of the field. The positive ions made up of the nuclei and the bound electrons remain held in the fixed positions. In electrolytic conductors, the charge carriers are both positive and negative ions. But the situation in this case is more involved. The movement of the charge carriers is affected by external electric field as also by the so-called chemical forces. See chapter 3. We shall restrict our discussions to metallic solid conductors. Let us note important results regarding electrostatics of conductors. 1. Inside a conductor, electrostatic field is 0. Consider a conductor neutral or charged. There may also be external electrostatic field in the static situation. When there is no current inside or on the surface of the conductor, the electric field is 0 everywhere inside the conductor. This fact can be taken as the defining property of a conductor. A conductor has free electrons. As long as electric field is not 0, the free charge carriers would experience force and drift. In the static situation, the free charges have so disturbed themselves that the electric field is 0 everywhere inside. Electrostatic field is 0 inside a conductor. 2. At the surface of charged conductor, electrostatic field must be normal to the surface at every point. If vector E were not normal to the surface, it would have some non-zero component along the surface. Free charges on the surface of the conductor would then experience force and move. In the static situation, therefore, E should have no tangential component. Thus, electrostatic field at the surface of a charged conductor must be normal to the surface at every point. For a conductor without any surface charge density, field is 0 even at the surface. See result 5. 3. The interior of a conductor can have no excess charge in the static situation. A neutral conductor has equal amounts of positive and negative charges in every small volume of surface element. When the conductor is charged, the excess charge can reside only on the surface in the static situation. This follows from the Gauss law. Consider any arbitrary volume element V inside a conductor. On the closed surface S bounding the volume element V, electrostatic field is 0. Thus, the total electric field through S is 0. Hence, by Gauss law, there is no net charge enclosed by S. But the surface charges can be made as small as you like. That is, the volume V can be made vanishingly small. This means there is no net charge at any point inside the conductor, and any excess charge must reside at the surface. 4. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. This follows from the result 1 and 2 above. Since E is equal to 0 inside the conductor and has no tangential component on the surface, no work is done in moving a small test charge within the conductor and on its surface. That is, there is no potential difference between any 2 points inside or on the surface of the conductor. Hence, the result: if the conductor is charged, electric field normal to the surface exists. This means potential will be different for the surface and a point just outside the surface. In a system of conductors of arbitrary size, shape and charge configuration, each conductor is characterized by a constant value of potential, but this constant may differ from one conductor to another. 5. Electric field at the surface of a charged conductor. E is equal to sigma by epsilon 0 into n cap, where sigma is the surface charge density and n cap is a unit vector normal to the surface in the outward direction. To derive the result, choose a pillbox, a short cylinder, as the Gaussian surface about any point P on the surface, as shown in figure 2.17. The pillbox is partly inside and partly outside the surface of the conductor. It has small area of cross section, delta S, and negligible height. Just inside the surface, electrostatic field is 0. Just outside the field is normal and to the surface with its magnitude E. Thus, the contribution to the total flux through the pillbox come only from the outside, that is circular cross section of the pillbox. This equals plus or minus E delta S, positive for sigma greater than 0, negative for sigma less than 0. Since over the small area delta S, E may be considered constant and E and delta S are parallel or anti-parallel, the charge enclosed by the pillbox is sigma delta S. By Gauss law, E delta S is equal to sigma into delta S divided by E0. E is equal to sigma by epsilon 0. Including the fact that electric field is normal to the surface, we get the vector relation equation 2.35, which is true for both signs of sigma. For sigma greater than 0, electric field is normal to the surface outward. For sigma less than 0, electric field is normal to the surface inside. 6. Electrostatic shielding. Consider a conductor with a cavity with no charges inside the cavity. A remarkable result is that the electric field inside the cavity is zero. Whatever be the size and shape of the cavity and whatever be the charge on the conductor and external fields in which it might be placed, we have proven a simple case of this result already. The electric field inside a charged spherical shell is zero. The proof of the result for the shell makes use of the spherical symmetry of the shell. See chapter 1. But the vanishing of the electric field in the charge-free cavity of a conductor is as mentioned above, a very general result. A related result is that even if the conductor is charged or charges are induced on neutral conductor by an external field, all charges reside only on the outer surface of the conductor with the cavity. The proofs of the result noted in figure 2.18 are omitted here, but we note their important implications. Whatever be the charge and field configuration outside, any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always zero. This is known as electrostatic shielding. The effect can be made use of in protecting sensitive instruments from outside electrical influence. Figure 2.19 gives summary of the important electrostatic properties. 2.10 Dielectrics and polarization. Dielectrics are non-conducting substances. In contrast to conductors, they have no or negligible number of charge carriers. Recall from section 2.9 what happens when a conductor is placed in an external electric field. The free charge carriers move and charge distribution in the conductor adjusts itself in such a way that the electric field due to induced charges opposes the electric field within the conductor. This happens until in the static situation two fields cancel each other and net electrostatic field in the conductor is zero. In a dielectric, this free movement of charges is not possible. It turns out that the electric field induces dipole moment by stretching or reorienting molecules of the dielectric. The collective effect of all the molecular dipole moments is net charge on the surface of the dielectric, which produce a field that opposes the external field. Unlike in a conductor, however, the opposing field so induced does not exactly cancel the external field. It only reduces it. The extent of the effect depends on the nature of the dielectric. To understand the effect, we need to look at the charge distribution of a dielectric at the molecular level. Molecules of a substance may be polar or non-polar. In a non-polar molecule, the centers of the positive and negative charges coincide. The molecule then has no permanent or intrinsic dipole moment. Examples of non-polar molecules are oxygen and hydrogen, molecules which because of their symmetry have no dipole moment. On the other hand, a polar molecule is one in which the centers of positive and negative charges are separated even when there is no external field. Such molecules have a permanent dipole moment. An ionic molecule such as HCl or molecule of water H2O are examples of polar molecules. In an external electric field, the positive and negative charges of non-polar molecule are displaced in opposite directions. The displacement stops when external force on the constituent charges of the molecule is balanced by the restoring force due to internal fields in the molecule. The non-polar molecule thus develops an induced dipole moment. The dielectric is said to be polarized by external field. We consider only the simple situation when the induced dipole moment in the direction of the field and is proportional to the field strength. Substances for which this assumption is true are called linear isotropic dielectrics. The induced dipole moments of different molecules add up, giving a net dipole moment of the dielectric in the presence of external field. A dielectric with the polar molecules also develops a net dipole moment in the external field, but for a different reason. In the absence of any external field, the different permanent dipoles are oriented randomly due to thermal agitation, so the total dipole moment is zero. When an external field is applied, individual dipole moments tend to align with the field. When summed overall the molecules, there is then a net dipole moment in the direction of the electric field. That is, dielectric is polarized. The extent of polarization depends on the relative strength of two mutually opposite factors. The dipole potential energy in the external field tending to align the dipoles with the field, and thermal energy tending to disrupt the alignment. There may be, in addition, the induced dipole moment effect as for non-polar molecules, but generally the alignment effect is more important for polar molecules. Thus, in either case, whether polar or non-polar, a dielectric develops a net dipole moment in the presence of an external electric field. The dipole moment per unit volume is called polarization and is denoted by P. For linear isotropic dielectrics, P is equal to chi E into E, where chi E is a constant characteristic of dielectric and is known as electric susceptibility of the dielectric medium. It is possible to relate chi E to the molecular properties of the substance. We shall not pursue that here. The question is, how does a polarized dielectric modify the original external field inside it? Let us consider for simplicity a rectangular dielectric slab placed in a uniform external electric field parallel to two of its faces. The field causes a uniform polarization P of the dielectric. Every volume element delta V of the slab has a dipole moment P delta V in the direction of the field. The volume element at delta V is macroscopically small but contains a very large number of molecular dipoles. Anywhere inside the dielectric, the volume element delta V has no net charge through it, though it has net dipole moment. Thus, this is because the positive charge of the dipole sits close to the negative charge of the adjacent dipole. However, at the surface of the dielectric normal to the electric field, there is evidently a net charge density, as seen in figure 2.23. The positive ends of the dipole remain unneutralized at the right surface and negative ends at the left surface. The unbalanced charges are induced charges due to external field. Thus, a polarized dielectric is equivalent to two charged surfaces with induced surface charge densities, say sigma p and minus sigma p. Clearly, the field produced by these surface charges opposes the external field. The total field in the dielectric is thereby reduced. From the case when no dielectric is present, we should note that the surface charge density plus or minus sigma p arises from bound, not free charges in the dielectric. 2.11 Capacitors and capacitance. A capacitor is a system of two conductors separated by an insulator, figure 2.24. The conductors have charges, say capital Q1 and capital Q2, and potentials, say V1 and V2. Usually in practice, the two conductors have charges Q and minus Q with potential difference V is equal to V1 minus V2 between them. We shall consider only this kind of charge configuration of the capacitor. Even a single conductor can be used as a capacitor by assuming that the other at infinity. The conductors may also be charged by connecting them to the two terminals of the battery. Q is called the charge of the capacitor, though in fact this is the charge on one of the conductors. The total charge of the capacitor is 0. The electric field in the region between the conductors is proportional to the charge capital Q. That is, if the charge on the capacitor is say doubled, the electric field will also be doubled at every point. This follows from the direct proportionality between field and charge implied by Coulomb's law and the superposition of principle. Now, potential difference V is the work done per unit positive charge in taking small test charge from the conductor 2 to 1 against the field. Consequently, V potential is also proportional to Q, and the ratio Q by V is a constant. C is equal to Q by V. The constant C is called capacitance of the capacitor. C is independent of Q or V as stated above. The capacitance C depends only on the geometrical configuration, that is shape, size and separation of the system of two conductors. As we shall see later, it also depends on the nature of the insulator, that is dielectric, separating the two conductors. The SI unit of capacitance is 1 farad equal to 1 coulomb volt raised to minus 1. A capacitor with a fixed capacitance is symbolically shown as this, while the one with variable capacitance is shown with this. Equation 2.38 shows that for large capacitance, potential is small for a given charge. This means a capacitor with a large capacitance can hold a large amount of charge Q at a relatively small V. This is for practical importance. High potential difference implies strong electric field around the conductors. A strong electric field can ionize the surroundings air and accelerate the charges so produced to the oppositely charged plates nearby, neutralizing the charge on the capacitor plates at least partly. In other words, the charge of the capacitor leaks away due to the reduction of insulating power of intervening medium. The maximum electric field at a dielectric medium can withstand without breaking down of its insulating properties called as dielectric strength. For air, it is about 3 × 10⁶ volt per meter. For a separation between conductors of the order 1 cm or so, this field corresponds to a potential difference of 3 × 10⁴ volt between the conductors. Thus, for a capacitor to store a large amount of charge without leaking, its capacitance should be high enough so that the potential difference and hence the electric field do not exceed the breakdown limits. Put differently, there is a limit to the amount of charge that can be stored in a given capacitor without significant leaking. In practice, a farad is a very big unit. The most common units are its submultiples like 1 microfarad is equal to 10⁻⁻⁶ farad, 1 nanofarad is equal to 10⁻⁹ farad, 1 picofarad is equal to 10⁻12 farad, etc. Besides this, its use in storing charge, a capacitor is a key element of most AC circuits with important functions as described in chapter 7. 2.12 The parallel plate capacitor. A parallel plate capacitor consists of two large plain parallel conducting plates separated by a small distance. We first take the intervening medium between the plates to vacuum. The effect of a dielectric medium between the plates is discussed in the next section. Let A be the area of each plate and D be the separation between them. The two plates have charges plus the capital Q and minus capital Q. Since small d is smaller than linear dimensions of the plates, d square very less than A, we can use the result on dielectric field by an infinite plane sheet of uniform surface charge density. Plate 1 has surface charge density of sigma is equal to Q by A, and plate 2 has surface charge density of minus sigma is equal to minus Q by A obviously. The electric field in different regions is outer region 1 is equal to sigma by 2 epsilon 0 minus sigma by 2 epsilon 0 is equal to 0. Outer region 2, region below the plate 2, is equal to sigma by 2 epsilon 0 minus sigma by 2 epsilon 0 equal to 0. In the inner region between the plates 1 and 2, the electric field due to the two charged plates add up, giving E is equal to sigma by 2 epsilon 0 plus sigma by 2 epsilon 0 is equal to sigma by epsilon 0 plus Q by epsilon 0 into A. The direction of the electric field is from positive to negative plate. Thus, electric field is localized between the two plates and is uniform throughout. For plates with finite area, this will not be true near the outer boundaries of the plates. The field lines bend towards at the edges, an effect called the fringing of the field. By the same token, sigma will not be strictly uniform on the entire plate. E and sigma are related by equation 2.35. However, for d square very much less than A, these effects can be ignored in the regions sufficiently far from the edges, and the field here is given by equation 2.41. Now for uniform electric field, potential difference is simply electric field times the distance between the plates. V is equal to ED is equal to 1 by epsilon 0 QD divided by A. The capacitance C of the parallel plate capacitor is then C is equal to Q by V is equal to epsilon 0 A by D, which as expected depends only on the geometry of the system. For typical values like A is equal to 1 meter square, D is equal to 1 millimeter, we get C is equal to 8.85 into 10 raised to minus 12 C square n raised to minus 1 m raised to minus 2 into 1 meter square divided by 10 raised to minus 3 meter is equal to 8.85 into 10 raised to minus 9 farad. You can check that if 1 farad is equal to 1 coulomb volt inverse, 1 is equal to 1 coulomb is equal to 1 coulomb square Newton raised to minus 1 meter raised to minus 1. This shows that 1 farad is too big a unit in practice as remarked earlier. Another way of seeing the bigness of 1 farad is to calculate the area of the plates needed to have C is equal to 1 farad for a separation of say 1 centimeter. A is equal to CD by epsilon 0 equal to 1 farad into 10 raised to minus 2 meter divided by 8.85 into 10 raised to minus 12 C square n raised to minus 1 m raised to minus 2 is equal to 10 raised to 9 meter square, which is a plate about 30 kilometer in length and breadth. 2.13 Effect of dielectric on capacitance. With the understanding of the behavior of dielectrics in an external field developed in section 2.10, let us see how the capacitance of a parallel plate capacitor is modified when a dielectric is present. As before, when have two large plates, each of area A, separated by distance d, the charge on the plate is plus or minus q, corresponding to the charge density plus or minus sigma, with sigma equal to q by A when there is a vacuum between the plates. epsilon 0 is equal to sigma by, E0 is equal to sigma by epsilon 0. And the potential difference of V0 is equal to E0 into D. The capacitance C0 in this case is C0 is equal to Q divided by V0 is equal to epsilon 0 A by D. Consider the next dielectric inserted between the plates fully occupying the intervening region. The dielectric is polarized by the field, and as explained in section 2.10, effect is equivalent to two charged sheets at the surface of the dielectric normal to the field with the surface charge density sigma p and minus sigma p. The electric field in the dielectric then corresponds to the case when the net surface charge density on the plate is plus minus bracket sigma minus sigma p, that is E is equal to sigma minus sigma p divided by epsilon 0, so that potential difference across the plate is V is equal to ED is equal to sigma minus sigma p divided by epsilon 0 into D. For linear dielectrics, we expect sigma p to be proportional to E0, that is to sigma. Thus sigma minus sigma p is proportional to sigma, and we can write sigma minus sigma p is equal to sigma by k, where k is a constant characteristic of dielectric. Clearly k is greater than 1. We then have V is equal to sigma d by epsilon 0 k. The capacitance C with the dielectric between the plates is then C is equal to Q by V is equal to epsilon 0 K A divided by D. The product epsilon 0 K is called permittivity of the medium and is denoted by epsilon. Epsilon is equal to epsilon 0 K. For vacuum, K is equal to 1 and epsilon is equal to epsilon 0. Epsilon 0 is called the permittivity of the vacuum. The dimensionless ratio K is equal to E by epsilon 0 divided by epsilon 0 is called the dielectric constant of the substance. As remarked before from equation 2.49, it's clear that K is greater than 1. From equations 2.46 and 2.51, K is equal to C by C0, or C is equal to, you can write C0 into K. Thus dielectric constant is the factor greater than 1 by which the capacitance increases from its vacuum value when the dielectric is inserted fully between the plates of a capacitor. Though we arrived at equation 2.54 for the case of parallel plate capacitor, it holds good for any type of capacitor and can in fact be viewed in general as a definition of the dielectric constant of a substance. Combination of capacitors 2.14. We can combine several capacitors of capacitance C1, C2, etc. Cn to obtain a system with some effective capacitance C. The effective capacitance depends on the way the individual capacitors are combined. Two simple possibilities are discussed below. 2.14.1 Capacitors in series. Figure 2.26 shows the capacitors C1 and C2 combined in series. The left plate of C1 and the right plate of C2 are connected to terminals of the battery and have charges plus Q and minus Q respectively. It then follows that the right plate of C1 has charge minus Q and the left plate has charge plus Q. If this was not so, the net charge on each capacitor would not be 0. This would result in the electric field in the conductor connecting C1 and C2. Charge would flow until the net charge on both C1 and C2 is 0 and there is no electric field in the conductor connecting C1 and C2. Thus, in the series combination, charges on the two plates plus minus Q are the same on each capacitor. The total potential drop V across the combination is the sum of the potential drops V1 and V2 across C1 and C2 respectively. Therefore, V is equal to V1 plus V2 is equal to Q by C1 plus Q by C2. That is V by Q is equal to 1 by C1 plus 1 by C2. Now we can regard the combination as an effective capacitor with a charge Q and potential difference V. The effective capacitance of the combination is C is equal to Q by V. We obtain 1 by C is equal to 1 by C1 plus 1 by C2. The proof clearly goes through for any number of capacitor arranged in a similar way. Equation 2.55 for n capacitors arranged in series generalizes to V is equal to V1 plus V2 plus etc. Vn is equal to Q by C1 plus Q by C2 plus etc. plus Q by Cn. Following the same steps as for the case of two capacitor, we get general formula for effective capacitance of a series combination like 1 by C plus 1 by C1 plus 1 by C2 plus 1 by C3 etc. gives 1 by Cn. 2.14.2 capacitors in parallel. Figure 2.28a shows two capacitors arranged in parallel. In this case, the same potential difference is applied across both the capacitors, but the plate charges plus minus Q1 on capacitor 1 and the plate charges plus minus Q2 on the capacitor 2 are not necessarily the same. Q1 is equal to C1V, Q2 is equal to C2V. The equivalent capacitor is 1 with the charge Q is equal to Q1 plus Q2 and potential difference capital V. Q is equal to C by V is equal to C1V plus C2V. The effective capacitance C is from equation is C is equal to C1 plus C2. General formula for effective capacitance C for parallel combination of n capacitor follows similarly. Q is equal to Q1 plus Q2 plus etc. plus Qn. That is CV is equal to C1V plus C2V plus etc. CNV, which gives C is equal to C1 plus C2 plus etc. Cn. 2.15 Energy stored in capacitor. A capacitor, as we have seen above, is a system of two conductors with charge Q and minus Q. To determine the energy stored in this configuration, consider initially two uncharged conductors 1 and 2. Imagine next a process of transferring charge from conductor 2 to conductor 1 bit by bit so that at the end conductor 1 gets charge Q. By charge conservation, conductor 2 has charge minus Q at the end. In transferring positive charge from conductor 2 to conductor 1, work will be done externally. Since at any stage conductor 1 is a higher potential than conductor 2, to calculate the total work done, we first calculate the work done in small steps involving transfer of an infinitesimal, that is vanishingly small amount of charge. Consider the intermediate situation when the conductors 1 and 2 have charges Q dash and minus Q dash respectively. At this stage, the potential difference V dash between the conductors 1 to 2 is Q dash by C, where C is the capacitance of the system. Next, imagine that a small charge delta Q dash is transferred from Q2 to Q1. Work done in this step delta W dash resulting in the charge Q dash on conductor 1 increasing to Q dash plus delta Q dash is given by delta W is equal to V dash into delta Q is equal to Q dash by C into delta Q dash. Integration equation 2.68 we get W is equal to integral 0 to Q dash by C delta Q is equal to 1 by C Q dash square by 2 from limit 0 to Q is equal to Q square by 2C. We can write the final results in different way. W is equal to Q square by 2C is equal to 1 by C V square is equal to 1 by 2 QV. Since the electrostatic force is conservative, this work is stored in the form of potential energy of the system. For the same reason, the final result for potential energy is independent of the manner in which the charge configuration of the capacitor is built up. When the capacitor discharges, stored up energy is released. It is possible to view the potential energy of the capacitor as stored in the electric field between the plates. To see this, consider for simplicity a parallel plate capacitor of area A of this plate and separation D between the plates. So energy stored in the capacitor will be half Q square by C is equal to A sigma whole square by 2 into D by epsilon 0 A. The surface charge density sigma is related to the electric field E between the plates. E is equal to sigma by epsilon 0. So from equations we get energy stored in the capacitor U is equal to half epsilon 0 E square into AD. Note that AD is the volume of the region between the plates where electric field alone exists. If we define energy density as energy stored per unit volume of space, shows that energy density of the electric field U is equal to half epsilon 0 E square. Though we derive equation for the case of parallel plate capacitor, the result on the energy density of an electric field is in fact very general and holds true for electric field due to any configuration of charges. So that's all for the whole chapter audiobook. Thank you for watching. Please do subscribe our channel and support us, and do comment in the comment section below if the class was useful and in what ways I have to improve my content. So thanks for watching. Take care and bye.